Yeah, hi everyone. So my name is Jiaming. So I'm the chief scientist at Luma AI. We are a multimodal intelligence company, and in currently we have built like many different product and applications in the multimodal domain, starting with 3D reconstruction, which started as in the case of a phone app where you can go do like 3D scanning, and then we went on to do 3D generation in the form of Genie, and then we went on to build a intelligent creative partner called Dream Machine, and which has image generation, video generation capabilities. Recently, we released a video model called Ray 2, and this allows you to do many different features such as like text to video, image to video, keyframes, and so on. So yeah, but in like what we care about is like what is the long-term problem that is going to be the next big thing in multimodal intelligence. And today I'm very happy to kind of share a little bit more about our like developments and our thinking about on this field, and especially especially on this in this case. Yeah. So I worked from more of a background on diffusion models and research. I actually did one of the earliest work on like fast diffusion model sampling called denoising diffusion implicit models when I was a PhD at Stanford. So I was like always deeply interested in this, like the algorithm developments of this field. So, and as of today, 5 years later, diffusion models are kind of a very key part of AI, creation. So these are some examples from our like way to image to video techniques. So we can actually, now what has kind of been unimaginable like 2 years ago are like possible. You can animate, emojis, memes, or anything you want. However, the problem is that these kind of workflows are not as intelligent as language models. You wouldn't be expecting it to, execute very complex workflows, or unless you develop, a bunch of control nets or a bunch of, like LoRa's and so on. So in the current creation workflow, it is not as like simple as, language model where many things can just be done in context learning. So this is the, current status quo, and where basically, the method has been stagnating for almost 5 years. So around May 2020, the GPT-3 paper came out, which kind of sets autoregressive for discrete tokens as the regular standard for large language models. And at around that time, the paper called Denoising Diffusion Probabilistic Model came out, which is kind of the first kind of proof of concept that diffusion models is also, quite scalable and like high performance versus, other alternatives such as scans. So this paper came also around like June 2020. And if you look about it, like, these mathematical foundations has been there like for 5 years, and there has been much really in the community since. To give you a high-level overview of like what diffusion model does, so it basically, tries to build this interpolation between the data and noise. So, as you add more and more noise, this, cat image becomes more and more noisy. And then, what diffusion model does is essentially starting from, pure noise and gradually run this denoising process. Eventually, you will reach, a good-looking image or, in certain cases, good-looking video. However, a key problem is that in diffusion models, it requires, many time steps to converge. So this is kind of not good. So of course, people are thinking about the ways to make these like diffusion models more intelligent, and they try to kind of combine more like large language models, together. However, this hasn't been like super mainstream just of yet. This is an example from like DeepSeek called JANAS-Flow, where they try to unify the paradigm of autoregressive and like diffusion models for both understanding and generating capabilities for multimodal. One problem is like that. So basically, suppose your sequence is kind of a mixed, text, image, or video, or like multimodal tokens. Suppose it looks like this. So there's some discrete text tokens, some continuous tokens, and some discrete tokens, and then some continuous tokens. However, on the hardware, because the diffusion models requires many steps to converge, it will actually look like this. So you have like, the discrete tokens going one pass through the transformer. However, the diffusion models go through many passes through the transformer, which is actually quite, inefficient. On the other hand, the acceleration methods such as like distillation or consistency models are quite unstable to train in practice. So our goal is to kind of look into if there are like algorithm breakthroughs on modeling these continuous signals where diffusion models currently excel at, and address the kind of a efficiency, stability like dichotomy on this field. So if you want efficiency, currently you have to work with unstable training like distillation, or with the diffusion model, which is stable, you have to work with its inefficiencies. So basically, our goal is to hope to have better efficiency and better like stability all in one model. And this is where this our technique called like inductive moment matching comes in. And we released this as a archive paper, and we open sourced the weights last week for research purposes. And it has all the benefits of diffusion models. So inference time scaling, meaning that you run it more steps, the quality gets better. It is very stable to train, and it also gives you very high quality generation. And the key is that as this number of steps goes to infinity, this should be on par with diffusion models, but the quality of our method is much better than diffusion models on like fewer number of steps. As you can see here, if you have more steps, it converges to the same point, but with fewer steps, it's better. So here's the kind of a training stability showing of this versus consistency model. So consistency model is also an attempt to address this kind of efficiency problems for diffusion models, but the training of the consistency models on tasks like ImageNet is quite unstable, and it doesn't really work super well for like various like architecture design choices. And we can also show that on this axis, the sampling compute on this x-axis and the pressure interception distance on the y-axis. So here we want to use like fewer sampling compute to reach a lower distance. So basically, towards the lower left is better. And you can see that like diffusion models is on this corner where sampling is very long. Consistency model is on this corner where it's pretty fast, but the quality is not that great. Autoregressive model is somewhere in between, and like IMM, our methods kind of like in the frontier right now. So like I know this is not a super technical audience, but I want to kind of give a very, very high level overview of like what is the idea behind this, and how it is like different from like some aspects of diffusion models. So to start with, we want two things. One is that we want inference time scaling, so that still we have running it more steps gives us like higher quality samples, which is something that diffusion model does. On the other hand, if the model has enough capacity, then we should use as fewer steps as possible. So this is something of a property similar to a GAN, where you can just like have a big enough model and run it in one step. And the limit, like to analyze why like the IMM, how IMM works, we kind of try to analyze maybe one of the most popular diffusion inference algorithm, DDIM, which I kind of also wrote together with Stefano. So DDIM as the sampler works like this. So suppose you are given the current noisy sample at a certain time step, which is basically a time step means the ratio between the data and the noise. And you are going to denoise to the next time step, which gives you a slightly less noisy sample. So on the whole, the sampling process, one-step sampling process of DDIM is a function of the current sample, the current time step, and the next time step. However, the diffusion model alone only takes in two arguments, which is the current sample and the current time step. So with respect to the next time step, which this DDIM is also a function of, this DDIM is actually a linear function. So you can see here that once we have trained the diffusion model, you can select to skip different number of steps in this process. Of course, more steps gives you better performance, and that's what we all choose. But you don't have actually a lot of flexibility in terms of like how the model changes with the next step. So you can see that here this is a linear function, and it's obviously quite bad if you want to achieve both one step kind of a convergence and like many step convergence. So the fix is actually quite simple. So you can just have the model to also take in the next time step, and it will basically ask the neural network to represent this like as a much more flexible function. And the idea is that here, the function of the next time step is much more stable, and therefore, I can use this to represent, much more flexible functions than what the original DDIM method could be done. Of course, we can't train it with the regular diffusion models anymore because we changed the network definition, but actually it can be done with a pretty stable kind of method called moment matching. So we are mostly using a form of moment matching called maximum mean discrepancy. It is kind of like a GAN, but it is using something called the kernel functions as the discriminator. So the high-level idea is that with this special set of functions as a discriminator, we don't actually need to materialize the discriminator. Instead, we can just compute the maximum part of the discriminator is effectively with kernels. So there's no need to kind of train your discriminator, because assuming that my function space is defined by this, you can just use kernels to represent the discriminator result. At a high level, it's kind of like, suppose I have two distributions and I want to kind of compare the distances, I will, suppose I have a distribution of dogs and a distribution of fish. So the idea of the kernels is just that I compute the kernel distance between all the dogs and plus that of all the fishes, and then I minus that across the different distributions. So if you try to minimize this, what it on the high level does is that it tries to kind of have an attraction force between the two distributions and have a repulsive force that kind of pushes the samples away within each distribution. So that's kind of how moment matching on the high level works. This is a figure that shows that first of all, IMM is a more stable version of consistency model, and it also happens to kind of be connected to consistency model in the sense that consistency models is actually just IMM, but we are using, if you're only using one sample to compare the two distributions. Of course, a distribution is more complex and it has multiple samples, so comparing only one sample of them is probably less accurate, and therefore it has less stability here. So overall, we hope that with this new approach, we can see better trade-offs for inference time scaling, meaning that we can still scale on the inference axis, but you have the stability of diffusion while the efficiency of distillation at the same time. So yeah, that's it. Thanks.
Thank you, Jamie. Super helpful. Very excited to unveil the research behind IMM. We'll take 2 to 3 questions. Hi. Yeah. Thank you very much for that. My favorite question: where do you get your video data set? I'm sorry. I know it's a tough one.
I think this is probably not the best. I'm probably not the best person to ask this. So I'm mostly working on the research side of things, and usually these are data sets that are in the public domain, such as say UCF 101, or these kind of this is like a public research data that they can use to do academic research and such.
Thank you. I kind of just curious, for Dream Machine, right? The adoption stage for the IMM to go into the next Dream Machine, how long that duration will look like, and even on the research side, what the next iteration for IMM will look like.
So I think there's multiple ways of doing it. One is to start training from scratch, which will obviously take a bit longer of time. So we have demonstrated very good capabilities of training from scratch on medium-sized problems, but I think it will take a little bit of time of development to move to the next stage, which is large-scale text-to-image and text-to-video models. But I think the attractiveness of this is that once this works, then it can be. I believe that this can be used for for other workflows quite immediately, like control nets and LoRa's. And I feel like these kind of existing workflows that people have built on diffusion models should just work. So we are also planning to release the training code once it gets more mature soon. Yeah.
Cool. Thank you. Thank you so much, Jimmy. Really appreciate it. Yeah.